Hello everybody, this is the second lesson for this week. Again, I hope you're all safe and well and keeping out of trouble at home. Today's lesson then is called Mass versus Weight, and we have three objectives. I can define centre of mass, I can explain the difference between mass and weight, and I can calculate weight on different planets. And that one's pretty cool. I was walking through Frome not too long ago, and I walked past the Memorial Theatre, and I noticed there was a statue there. And whenever I walk through a city, I don't really take much notice of the statues. But this one, I decided to find out a little bit more about it. So I thought it looked a little bit, he's dressed up in a World War uniform, and he's outside the Memorial Theatre, and I just wanted to know a bit more about it. But this is actually Sergeant Charlie Robbins. He worked at the J.W. Singer Foundry, and that's where the statue was. No one really knew much about it. The people in Frome made an appeal and found out it's really important information that he served during World War One, and eventually the statue was moved and placed outside the Memorial Theatre, and I'm sure you've seen him. So I thought I'd give him a little bit of respect and use him in the beginning of our lesson for today. So this statue, I reckon, is made up of about 100 trillion atoms. I don't actually know. I'm never going to be able to count them all. There are far too many. But a nice round number, I reckon, about 100 trillion atoms. Mass is a science word we use which tells us how much matter there is inside something. We can't use number of atoms because that 100 trillion, it just loses any meaning. I mean, we can't go around saying this is 100 trillion, this is 50 trillion, it's 100 trillion, 79 billion, 60 million. The numbers are just far too big and it doesn't really make any sense. So we can't use number of atoms to represent mass, so we use this constant called kilograms. And kilograms is something we know a little bit more about. So on Earth, Charlie Robbins is made up of about 100 trillion atoms, and this is a mass of 250 kilograms. And that number 250 is much more manageable and it's much more easier to use than 100 trillion. So mass tells us how much matter there is in something. It tells us kind of how many atoms there are and how much matter there is inside something. So on Earth, Charlie Robbins has a mass of 250 kilograms. But what if Charlie Robbins wasn't on Earth? Would his mass change? So on Earth it's 250 kilograms. Would it change? Well, let's go find out. Let's put Charlie Robbins up on the moon. But guess what? He still has that 100 trillion atoms. So his mass is still 250 kilograms. Even on the moon, his mass doesn't change. His mass is the same. Everywhere that Charlie Robbins goes in the universe, he has a mass of 250 kilograms. And that's because he hasn't lost matter. The arms, the legs, the head, the base, it's all the same number of atoms. So the mass doesn't change. And it doesn't matter where we put that statue, anywhere in the entire universe, any planet, on any star, in any galaxy, the mass doesn't change. It's still 250 kilograms because the number of atoms inside it hasn't changed. And it's the same for you and me and a TV screen and an Xbox and a hairdryer and everything. So if you've got a mass of 70 kilograms on Earth and you go to the moon, you'll still have a mass of 70. If you went to Mars, you would still have a mass of 70 kilograms. And if you went to an alien, weird planet somewhere that we haven't discovered yet, and you went there, you would still have a mass of 70 kilograms. And that's because the amount of matter or the amount of stuff inside something hasn't changed. So we say mass does not change. And that's super, super important in understanding that. Mass doesn't change anywhere in the entire universe. So if you've got a 5 kilogram ball on the moon, 5 kilograms. On another planet, 5 kilograms. Out in space, 5 kilograms. The mass doesn't change. But weight does change. Weight does change. And there's an equation that's going to help us figure this out. So weight is equal to mass times the gravitational field strength. And we can write this as W equals M times G. And this time the letters are nice and easy. Weight begins with W, M begins with M, and gravitational field strength, the very first letter there is G. So W equals M times G. And physicists like me are quite lazy, and we're not going to write weight equals mass times gravitational field strength. It makes life so much easier if we use the letters, so W equals M times G. Use the correct letters in the equation. So W is a force, and it's measured in newtons. Now you might be thinking, oh, force, we did this last lesson and the lesson before. That's a vector quantity. So well done if you've thought about that. M is mass, and that's measured in kilograms always. And G is the gravitational field strength of the planet. So let's go back then to Charlie Robbins. Now on Earth, the gravitational field strength, or G, is 9.8 newtons per kilogram. 9.8 newtons per kilogram. And this means that for every single kilogram that something is, it is 9.8 times that in weight. So for Charlie Robbins, his mass is 250 kilograms. So let's see what his weight would be. So W equals M times G, weight equals mass times gravitational field strength. The weight is, the mass is 250 kilograms. Gravitational field strength is 9.8 newtons per kilogram. We times them together, and that gives us the weight, 2,450 newtons. So weight is mass times gravitational field strength. So we can say Charlie Robbins has a mass of 250 kilograms, or a weight of 2,450 newtons. Where did he go? Charlie Robbins has gone off to the moon. Now remember a minute ago, mass didn't change. If he was 250 kilograms on the Earth, then he was 250 kilogram mass on the moon. But does weight change? Well, the moon's gravitational field strength is a lot less than Earth. It's about a sixth as Earth. Here, gravitational field strength, or G, is only 1.6 newtons per kilogram. Now some people think there's no gravity on the moon. The moon's huge. It's about the quarter of the size of the Earth. It's absolutely massive. So of course, there is going to be some gravitational field strength there. And instead of 9.8 like it is on Earth, it's only 1.6 on the moon. So let's look at the sun. Weight is M times G. We know its mass is 250 kilograms. That doesn't change. But G here is different. It's 1.6 newtons for every kilogram. So you times 250 times 1.6, and it comes out as 400 newtons. And that's a lot less. His weight is a lot less on the moon than it was on the Earth. So his weight has changed, but his mass hasn't. Let's have a look on Mars. There he is. Oh, he's gone green like an alien now. So on Mars, the gravitational field strength is 3.7 newtons per kilogram. So on Earth it was 9.8, the moon was 1.6, and Mars was 3.7. That means there's a little bit of a stronger gravitational field than the moon. So W equals M times G. W, the weight, equals 250 kilogram mass times the gravitational field strength, which was 3.7. And that gives us a weight of 925 newtons. So that was more than the moon, but less than Earth. So his mass didn't change, but you've seen from the Earth to the moon to Mars, Charlie Robbins statue, the weight has changed. And that's because gravitational field strength has changed on each planet or each moon. So recap, mass does not change, and weight is dependent on the gravitational field strength. So I suggest that you pause the video and you just write down that quick one sentence there. Right, let's go back to Froome then. So here's somewhere you might recognise. Bramble and Wild, nice for a flower shop this one. So this time you're going to have a go at calculating some weights for me. Sweet little dog there. I think she's called Rosie. Got some flower pots and we've got a notice board. So the chalkboard has a mass of 5 kilograms. Each flower pot has a mass of 1 kilogram, and Rosie the dog has a mass of 8 kilograms. Now we're on Earth. Okay, so what I want you to work out is the weights of the chalkboard, 1 flower pot, and Rosie the dog on Earth. And the gravitational field strength on Earth was 9.8 newtons per kilogram. So see if you can work out the weight. Right, let's have a look. So we use the equation W equals m times g. 5 kilogram chalkboard times 9.8, which is the gravitational field strength, and that gives us a weight of 49 newtons. How did you do? Now I do this thing called EMAU, E-M-A-U. E stands for equation, M for method, A for answer, U for unit. Equation, method, answer, unit. And it's really good practice to write out all of your sums in full. So the equation, W equals m times g. Method, you swap the letters for the numbers. In maths we call this substitution. A, the answer, 49, and U, the unit, newtons. Sometimes in the exam you'll lose a mark if you forget to put the unit. In this case it's N for newtons. You sometimes can lose a mark just for not putting the letter N afterwards. So email, equation, method, answer, unit. Always write out your sums in full. So if you've got weight equals 49 newtons, give yourself a tick. Well done. Let's look at a flower pot. So again, the equation, W equals m times g. 1 is the mass, 1 kilogram, and Earth's gravitational field strength is 9.8. So multiply those together and we get 9.8 newtons. Give it a tick if you got that one. And Rosie, 8 kilograms times 9.8 newtons per kilogram gives us a weight of 78.4 newtons. And again, give yourself a tick if you got Rosie's weight. So big task for you to do now. I found the gravitational field strengths for lots of bodies in our solar system and a couple beyond as well. So here they all are. Got the Sun, Mercury, Venus, Earth, Mars, all the way up to Enceladus, Vesta, and Gliese 581g. That's quite an interesting planet, that one. It's an exosolar planet, so it's a planet that exists outside of our solar system. It orbits a different star, so not our Sun. And some scientists think that there's liquid water there and an oxygen atmosphere, so perhaps there could be an alien life form on there. So something to look out for in the next few decades or so. 8 kilograms. Okay, and what I want to know is, there it is, mass is 8 kilograms. I want to know what the weight of Rosie the dog is on 5 of those celestial bodies of your choice. Okay, so Rosie went, for example, to Venus, to Pluto, to Ganymede, to Mars, to Io. What would Rosie's weight be? So you can choose 5 of your choice, and we'll go through the answers in a moment. So her mass is 8 kilograms. You know that doesn't change. The mass doesn't change. But what will her weight be on 5 different bodies? So pause the video and do your sums, equation, method, answer, unit. Write it all out in full and see what Rosie's weight is on 5 different bodies of your choice. So pause the video now. Right, let's have a look at some answers. Okay, so Rosie's weight, as you can see, on the Sun would be 2,344 newtons, Vesta on the right, 0.24 newtons. So what I did, I answered every single one for you so that you can see if you've got your answer right or not. So check your 5 that you chose and then give them a tick if you got them. If you got one wrong, you've got the answer here in front of you. So look at the answer and then try to figure out where you went wrong. So all you had to do was W equals m times g, mass was 8 kilograms, and then you times by the gravitational field strength of the celestial body. So my question to you here is, on which celestial body would Rosie's weight be most similar to Earth's? Now Earth is centre to the left. Rosie would have a weight of 78.4 newtons. So whereabouts out of all these bodies are these other planets and rocks would Rosie's weight be most similar to Earth's? So see if you can have a look. Okay, so there's Earth. And the answer would be Saturn or Uranus. So if Rosie went to Saturn, then her weight would almost be the same as it was on Earth. If she went to Uranus, it'd be almost the same as it was on Earth. So going from Frome College, finishing school, finishing college, and then going on to work in space must be pretty awesome. It wouldn't be surprising to me if more and more space-related jobs opened up in the next decade. You just got to look in the news or the Futurism app or something like that and see just what's going on in the world of space at the moment in the industry. And there's a lady here called Ariel Sandberg, and what she's doing at the moment I think is really, really interesting. She talks about her job and what she's working towards. So at the end of the video, click on the YouTube link and see what she's up to, and it might inspire you to want to go out and work out in space one day as well. So working in space requires you to understand a lot about science. If you want a satellite to orbit Earth, or you want to launch a rocket into space, we can't allow it to spin, because if it spins, it might crash. So here's a definition that you need to learn off by heart. The weight of an object may be considered to act at a single point, referred to as the object's centre of mass. So previously we've been drawing box and arrow diagrams, and if you were to draw weight, whereabouts on that box would that arrow start? So we say the weight can be considered to act from a single point. Appearing on the screen there. This is where all the weight acts, and if we apply a force to that centre of mass, so we push it where that centre is, where that red dot is, then you can see the satellite travels off without spinning. If we strike a force not at the centre of mass, then see what happens to the satellite now. Oh, it spins. That's no good. We don't want the satellite to spin. Now this is a device that you need to understand how it works and what it does. So a Newton meter is a device which measures the force of an object. You can hang an object onto it, gravity is going to pull the object down, and a spring in it is going to stretch. So there's our Newton meter there, it's just appeared on the right. And you can see there's a spring at the top and there's a hook at the bottom, and you attach objects to the hook. Gravity pulls the object down, which pulls the spring down, and you can see there's a scale with all numbers, like where the yellow part is, and as the hook gets pulled downwards by gravity, then you can see how much force the object has. So here I've got the left side is the yellow Newton meter, there's nothing on the hook, so we can see 0 newtons. And on the right one, we've got Isaac Newton's famous apple, the one where he was sitting under a tree and the apple landed on his head. I promise you it's the exact same apple. If you look at the scale, you can see it's about 1 Newton. So that would be the force. And that's because gravity is pulling the apple downwards, so that can be measured. So how is this all used in real life? Well, we know one day scientists are going to go to Mars, they might even go beyond as well. And then we need to understand what the gravitational field strength of different planets is. And what scientists now know is that if there's too much gravity, the gravitational field strength is too much, like on Jupiter for example, all our blood is going to be pulled down into our legs and we're going to be crushed. I've got a little pussycat there. Gravity set too high. Oh. And you can see that you're all going to be crushed. That's no good. That's no good for us human beings. We don't all want to be crushed. But if we went to a planet or a rock where the gravity was too little, the gravitational field strength was too small, Okay, so something perhaps like the moon or less so than the moon. We'll get headaches and our body produces too much blood. It goes into overdrive, produces too much blood, and our muscles become really, really weak. And you might have watched some movies where people go out into space and they have to do lots of extra exercise to strengthen their muscles, because as soon as you go out into zero gravity or low gravity field, then the muscles they start becoming weaker. There's nothing for them to work with. If there's no gravity, then they don't have to fight against it. So here's a Mars rover. Again, it's another really interesting video. And it's where NASA use gravimeters and like how they work out what the gravitational field strength of another planet actually is. So this video here that you can click on at the end of the video, you can actually see how do they work out the gravitational field strength of a planet. And there's a tiny little machine that uses something very similar to the Newton meter we were just looking at, and that's all it needs to work out the gravitational field strength of a planet. It's really, really interesting. I suggest that you watch that one, make some notes as you go. So here's some tasks then to end the lesson, as always. So define the terms mass and weight, which is a scalar, which is a vector, mass or weight. If you did a practical on Jupiter, what would happen on the Newton meter? So would it be pulled down more? Would it be pulled down less? See if you can think of a reason why. Task 4, you're in a class, the bell goes, you rush out of school, you go home, a real alien beams you up, takes you to Mars and Saturn, and takes you to home, where its home is Gliese 581G, before bringing you home. So draw a little comic strip, explain what's happening to your mass and your weight as you travel on your journey. And then task 5, as always, do the postcard physics, mass versus weight example calculations on the right hand side. I hope you found that interesting. Thank you very much. Take care, everyone.